Thank you all for being here. All right, extraterrestrial architecture. Now, it's a great time to be involved in space, right? Only a couple of months ago, Jeff Bezos unveiled his new spaceship to go back to the moon in a few years. And even Donald Trump got involved. He kind of pushing NASA to go back to the moon and, in a big way. So, Lockheed Martin really quickly is unleashing their new designs for their moon lander. Of course, they didn't expect that. Then Donald Trump says, no, we should not go to the moon. That's not what we're going to do. We did it 50 years ago. We're going to go to Mars. So he's maybe a bit confused where the moon and Mars is, what the difference is. But one that's not confused is, of course, Elon Musk, who is working really hard with his company SpaceX to really bring down the cost to space, right? And that's happening really, really fast, as you all been seeing. Now, he's also thinking about, just as Donald Trump, going to Mars. And what I find really interesting always about these kind of projects is that it's always about going there, and it's never about what's going to happen when we're there. You see all these kind of astronauts just came out, like, what are they going to do? Where are they going to live? So that's what I'm interested in, is I'm interested in what we're going to do, how we're going to live as astronauts, or inhabitants of another planet. The project I'll be talking about today is a project I've done for NASA's Centennial Challenge. It was a competition, and the idea was to look at how the first 4 astronauts would live on Mars and how we would design the habitat for that. Now, you might think, by the way, I'm an architect, so you might think, like, why is an architect involved in that? Isn't space, like, really technical? Look at the International Space Station. Isn't that a really complicated thing? Should architects be involved in that, really? It's just a big machine, right? And I think that's really the issue. I think looking at that, this is inside the International Space Station. I'm not sure, but you would want to live there for 6 months? I don't think I would. So I think designers and architects do have a role to play, I think, in space, and actually quite a central role. Now, I'm not the first architect or designer to kind of be interested in this and to actually work in space. Many years ago, 1973, even before I was born, Skylab. Skylab was the first space station from NASA. It was the first time astronauts were not traveling through space, but they were going to inhabit space. So Skylab was the first space station in orbit around the Earth, going around for not just days or hours or days, but really for weeks and months. So that was the first time NASA employed a designer. And that was this guy, Raymond Loewy. Yeah, quite a dude, right? He was an industrial designer, an American designer, and he was brought in by NASA to look at a few things for Skylab. He was asked to look at, first, the arrangement plan. He was asked to look at the noise levels, the light levels, and the color scheme. Now, he actually came in, and the engineers were a little bit skeptical about it. Now, what is this, designer coming to do? This is space. This is like serious stuff, right? It's not just about the colors, and not about making it pretty. Well, Raymond Loewy did actually change the colors. He did do that, but he did a couple of more things, which I think are actually crucial and actually show why designers should be involved in this field. First thing he did is Raymond Loewy designed a table. You might think, well, that's not that special, is it? A table? Well, the original design, the Skylab engineers, they designed just little tablets that would just kind of fold out from the side of the spaceship just at random locations. So there would not actually be a table. The astronauts could not have a conversation over a meal talking how their day went and what they're going to do next. So I think it's like quite a human perspective that they completely lost. Second thing Raymond Loewy brought in, you can see in the back, it's the window. Now, you might think, well, it's a window. What design, make it round? Or no. Actually, in the original design, the engineers did not put in a window, because for them, it was not necessary. Right? It was a weakness in the structure. So imagine being those 3 astronauts and going in orbit around Earth, and for weeks and months, never being able to look outside and to see this. I find that unimaginable almost. So You might think, well, NASA was not going to make that mistake again. Well, they kind of did, because this is the cupola, the most famous part in the International Space Station. And that took about 23 years to get installed, from original design to installation, because it got cost engineered each time out of the whole thing. So, but now is definitely the most famous part of the International Space Station, made it much more famous. Now, the distance of the International Space Station to Earth is about 400 kilometers. If you go into the moon, that's about 1,000 times that distance. And it took the Apollo astronauts about just over 3 days to get there. Now, if you're going to go to Mars, so this is a picture taken from Mars, from the Curiosity rover, quite if you see it there, and looking back to Earth. So Earth is just like a little speck on the sky. Again, that distance is 1,000 times the distance Earth-Moon. So it's actually really far. And it would take astronauts roughly just around a year to get there, depending on how you go. And that brings really some big issues, right? Because that distance makes it really expensive, right? And the cost is actually directly related to the mass and the volume you're bringing. So if you're going to go to Mars, what we're going to do is we're going to have to pack light. Right? So we put ourselves 3 kind of design principles to design our Mars habitat. First one was, indeed, pack light, compactable, as light as possible. Second, wherever we can, we're going to use local materials. Now, if we don't need to bring it with us, it's basically for free if we have it there. And the third thing is, whatever we bring, we better reuse it and recycle it as much as we can. Now, we wanted to get some inspiration of other pioneers. And the ones I thought was interesting to look at were these guys. Yeah? American pioneers, settlers, going west, finding new frontiers. They also had to travel light, use very simple ways to kind of inhabit, having little tents with them and all that. Only a few horses to kind of go across America. And then once they arrived there, they were using very simple techniques to build in these log cabins. Because they only had probably like an axe and a saw with them. So the simplest way to construct was to take logs, trunks, and actually put them on top of each other. There's no need to use complicated metalwork, no need for complicated woodwork. It was just stacking on top of each other. And it's that idea of using just the simplest material, not having any processing factories or anything like that, just whatever you find, using that material in the simplest way was kind of an inspiration for us. And I'll quickly show this video.
Half a century ago, we took our first step on the surface of the moon. Today, there is renewed passion to explore for our next human endeavor. Mars, the red planet, further than any human has ever been. We face many challenges: remoteness, no livable atmosphere, high radiation, dust storms, and extremely low temperatures. Before any humans set foot on Mars, we must first design a protective shelter. We will protect our astronauts from radiation with a thick 3D printed shell structure using Martian regolith, which works great in compression but does not perform well under tension. To overcome this shortfall, we have chosen to construct the pressure-retaining parts of the habitat from lightweight inflatable pods. They will be made out of high-precision engineered composites that are prefabricated on Earth. Their elliptoid geometry will be able to mitigate the pressure differences whilst optimizing spatial planning. To create the base on Mars, we will use a 2-phase approach. In Phase 1, an ecosystem of 3D printing robots will arrive months in advance of any human explorer. They will construct the protective shield for the base by adopting a modular robotic swarm strategy, a plan that allows for redundancies and enhances the odds for success. Intelligent autonomous robots will have interchangeable roles, from battery storage to scout rovers, logistics to excavational, and even 3D printing units, all integrated with multiple cameras and sensors for navigation. They can reconfigure themselves for a multitude of purposes, ensuring prolonged usage beyond the initial build phases. The smallest configuration is the one-wheeled Scout rover that uses ultrasonic scanning to analyze the Martian surface to determine the best regions for obtaining optimum regolith. The digger receives the location coordinates and then excavates the Martian soil. It then delivers the payload to the refining assemblies. Here, large chunks of Martian regolith can be processed down to a finer grain and then delivered to the melter robots in situ. They then use concentrated microwaves to melt the regolith and extrude through the 3D printing nozzle. The shell is autonomously 3D printed, layer by layer, over several months by the robotic system. In the next phase, the first astronauts arrive with the habitation units, equipment, and supplies. The robots now take on their second life roles to aid the next phase. They come together to make flexible mobile platforms that can carry the payload from the loading zone to the base. The convoy begins its journey across the Martian surface to the habitat site. The build commences with a connector module placed underneath the protective shield and ready for inflation. The module then unfolds and self-inflates into its final form. The habitation units are then placed into position and sequentially inflated to form the completed pressurized environments. The circular layout of the habitat ensures continuous accessibility of the habitat in the event of a catastrophic failure. Each connector module houses 3 integrated environmental control life support systems, delivering essential services like power, water, data, and oxygen to all the habitation units. A circular conduit delivers these services to multiple endpoints in each pod. The base will be remotely powered by 2 nuclear kilopower reactors and a solar farm, located a safe distance away from the base. In the next stage, the astronauts will construct and install a flat-pack, rail-based racking system capable of connecting to the distribution system, enabling spaces to reconfigure according to their spatial needs. This modular and radical design principle has been adopted for all the habitat pods, ensuring multi-use, reconfigurable environments. A Martian base should not just be a habitat. It is home for the astronauts. Each pod expresses its own identity, quality, and character. A highly functional design which places the human experience at the core. Spaces include a state-of-the-art research laboratory, a hydroponic greenhouse, a fully equipped workshop with digital fabrication facilities, the sleeping quarters with gym facilities, and immersive virtual reality platform. We believe that the key to success of human habitation on Mars is the health and well-being of its residents. Creating a place where work, life, and living combine holistically to ensure they feel connected to each other, to themselves, and somehow to their distant home.
So, let me go into this project a little bit in more detail. Yeah, can you just play this video? So, as architects, we got the brief from NASA, and the brief really stated that we had to 3D print a pressurized volume. Right. And being architects, we kind of question the brief. You know, architects tend to do that. They tend to question the brief of clients. They weren't kind of used to that. So we proposed that we are not going to 3D print a pressurized system. You know, I've worked in the past on large-scale 3D printing projects, and I know how difficult it is to really create something that is really with high tolerances. So what we decided, we have a double system. We have a 3D printed shell structure, and inside, which is in situ 3D printed, and inside we bring in these almost pop-up tents, which is manufactured on Earth with high manufacturing standards. And it's a little bit like, you know, it's quite an architectural way to do it, you know. Look at candela structures, you know. These are shell structures made in situ, not by robots, but by people, right? They have certain tolerances, not that accurate. And then afterwards, you bring in fit out, you bring in facade system, which is a much higher tolerance. So you kind of work with 2 systems at the same time. And that was our proposal. So quite an architectural approach to it. And then looking at the inflatables, well, you might think, oh, it's all good and well, you're kind of like coming up with these ideas, inflatables in space, But when we started the project, we really looked at using technology that is kind of almost there, yeah? That is kind of tested, that is not completely science fiction, right? So inflatables in space has happened before. This is NASA working with Goodyear in the early 1960s, looking at the first inflatable systems for space. And if you now look at the International Space Station, there is actually an inflatable module brought in. And that's a test module. It's very small, but here's an astronaut inside that module. So we're working towards these ideas to become more reality. Now, this of course is my favorite movie, The Martian. It's quite accurate. There are, although, a few bits that aren't that accurate, and it's just in the beginning where you have the big storm. The big storm happens, Matt Damon gets blown away across the Martian surface. Now, storms happen on Mars. They are very high speed. They're 200 kilometers an hour speed. They happen all over the planet as well. The only difference is that on Mars, the density of the atmosphere, mainly CO2, is about 100 times less than on Earth. So which means a 200 kilometers an hour wind only feels like a light breeze, so you could never be blown away. Now, that actually is a good thing for us, because which means if we design shell structures, that means we have very low wind loads, which means we have very low lateral forces, which means we can easily construct only pressure-containing structures. So, of course, we work with our engineers, Eckersley O'Callaghan, to design these, to make sure that there's no tension within these structures. So, so it was actually kind of an interesting way to work, and quite a pure way to work with a structure. Now, so we have these shell structures which are protecting us from gamma radiation, right? Now, that's all great, but remember that we wanted that view out. How do we do that? How do we kind of live in the shell structures but still have a view out? And instead of going for a really kind of complicated technical solution, we went for a quite architectural solution, right? Went for really something like this. Now a courtyard is a great system if you want to bring light in, but you don't want to get direct sunlight in. North Africa, you have these everywhere, beautiful courtyards. And on top of that, you create still a view across your habitat. And that's really what we did. We used the tools that we would use on Earth. We looked at solar radiation tools, making sure that not that we have direct sunlight, but that we don't have direct sunlight, not to get a tan or heat up your building or something like that, but really to not get cancer, because this radioactive gamma radiation that you would be affected by. So see, we're all in the blue, so we don't have any direct sunlight there, which is great. For this project, we decided to work with a huge range of collaborators. We opened up the project, brought in lots of people that we knew, anything from space anthropologists to mining professors to roboticists. The great thing, we worked with a guy called David Goodger from the British Antarctic Survey. Now that was really cool to work with them, because it's probably the closest to a Mars base. If you winterize on Halley 6 on the Antarctic, you would be cut away from the rest of civilization for about 8 months. Right? And we had long discussions with him. And one of the bits that I really picked up on was this. He said, you know what, the base is amazing and all that, but we're there for 8 months. And it's a bit that we were living in our own workplace. Right? It all looks a little bit like a lab. None of it really looks like a home. And so the guys there did something which I thought was hilarious. Look at the back there at the dartboards. So what they did this. So they took some of their crates, of the plywood crates that they had, packaging crates, and used that to then, do a bit of cladding. Make it a little bit more homey in a way, a bit more tactile materials. It doesn't look like a lab anymore immediately. So we looked at that and we used that. And of course, we're not going to bring crates and plywood, but we started to think and work with Cranfield University to start to think about growing bamboo. People think always, if you grow something on another planet, it's to feed yourself. Well, we don't think so. It might actually be better to grow something, to construct something, to build something. So we're using bamboo to then hopefully, as you kind of see, we're starting to do that, using some different finishes in the habitat, having some bamboo finishes. Now, The other thing is, you know what I said in the beginning, we're going to be light and reusing and recycling and all that. You see my big white sofa there, right? You think, well, that's not correct, right? We are going to reuse and recycle, and these chairs and the sofas are not really brought to Mars, but they are 3D printed. For that, we're working with another company called Nagami, and they do 3D printing of furniture. And we're envisioning now to use recycled plastics, packaging material from the habitat, to reuse those to start printing the furniture in the habitat. And you can see it happening on the back there. It's a Delta printer printing our furniture. And we're going a little bit further even. We thought, well, it's not about the furniture, but what are those astronauts going to wear? What are they? Should we recycle stuff there as well? So we started to work with Christopher Rabin, fashion designer based in Hackney, and all his stuff that he designs is always remade and recycled. So he uses existing material and makes it into something else. Even the jacket I'm wearing, this is made out of old German rain ponchos. And the back thing there, the jacket there, is actually made out of parachutes. So we're thinking maybe our astronauts, they could be wearing stuff made out of their landing parachutes. Who knows? And so we're working with him now, and he's actually kind of basing his latest collection on our design. So Earth is not my home. And so what's next? A lot of people ask me, so are you going to really build it, right, on Mars? So, well, no, that's quite a few years away. But we're moving further and further and developing a bit further. So one of the things we're doing now, that will happen in a few months, there's a great exhibition going on in the Design Museum, Moving to Mars. I love that, of course. And the next thing is that we're going to build a one-to-one mock-up of one of our pods, working together with different companies to see what it would be to live on Mars. So hopefully I can all see you there in the beginning of October. Thank you.
Thank you. Okay, we've got time for one question for Xavier. Do we have a question out there on the floor?
Interesting thing was the last time I saw your thing, you actually got a brains trust together to rip the crap out of your idea.
Oh, yeah.
That was like So they kind of designed it all, and then they just hired experts in all these different fields to come in and just tell them, this wouldn't work, this would work, and then you kind of refined it.
Well, it was kind of like we wanted to get lots of kind of, scientists and experts to come in and really, give some critique to it. And the way we did it, we organized a small symposium, like a private symposium, and then we did it what we know best as designers, do a design crit. So we pin it all up on the wall, have the scientists there for like 3 or 4 hours, get them to really criticize it and discuss it. And the great thing was, like, they really didn't agree as well, the scientists, on like really hard science facts. But it was fantastic. And what they thought was, it's an interesting process. They're not used to it.
Yeah.
So they're used to doing peer review papers and all that kind of stuff. They're not used to just being in a room and just kind of discussing in like an architectural crit.
Yeah, architectural crits are really only really ever held in architectural studios.
Normally, yeah.
Is there anyone got a question? Okay. Oh, sorry.
One down.
Hi, fantastic presentation. Really simple question though.
Yeah.
This is a few years off by your own admission, but the design process that you're going through, which is incredibly rigorous, but for a pretty tough environment and climate and economy of getting there, you need a lot of money to do it. What do you see as the potential, as it were, applications on Earth? I mean, you cited the British Antarctic Survey Station, I think it's Haley 5, that was built from that competition way back when. But do you see the economy, the rigor, the technical processes being applicable to building on Earth under similar conditions? Not that there are that many, but in places like Antarctic and Arctic.
Well, some bits are, I think, but I don't think we should design it with that in mind. Like I often get the question, like, okay, 3D printing these shell structures, wouldn't it be a great idea to do it on Earth? I thought, no, it's a terrible idea to do that. We have way better construction fabrication factories and methodologies to do that. You know, that's actually a terrible idea. That's a great idea on Mars, right? But it's not always applicable back. And I'm actually not driven by that. I don't think, because often you get that, like, the question is always now, so what is the application on Earth, right? The thing I learned really is more of an attitude is to, you know, whatever I bring, that's it. That's all I'm going to get. I need to do whatever I find, whatever. So for me, it was, in a really weird way, the most sustainable or super sustainable project I've ever worked on. And that made me start to think differently. So I think that's a great exercise to do. Some technologies will come back to Earth and find its applications, and other ones don't. But I don't think that has to be the driver always.
I think operating under constraints is a great thing. So I remember talking to an architect, I should remember his name, I can't, and he just said, architects don't know how much their buildings weigh. And I was like, whoa, that's like a deep thought. And he said, they don't know how much they weigh, and they don't know how much they can save by lightweighting their buildings, because you can save it in the foundations. And he made a business out of lightweighting buildings so he could save on the foundations, and he took a percentage of the difference he saved for the guys.
That's the way to do it. All right, thank you.
Okay, thanks very much.